All right, y'all. Let's talk about this. Caitlin, you all right there? No? Yes? Okay. I know these are going on up on the board, but just so we have this down in a video situation, which I think we're recording right now. Looks okay. All right, we've done nothing for the first few seconds. What's up? Yeah, man, why not? So Amos just did this one. But just to drop it in here, we are doing the quotient rule. So we do get this. No, we're not going to simplify this. We don't care about that. This is going to be negative cosecant x, cotangent x, all over. Okay. Can we handle that? Is that what Amos has? Looks good. Okay. For the second one, that's just a chain rule a handful of times. We'll do it up here. That's 1 over 2 square root ln of arc secant of x times the derivative of ln of arc secant. Well, that's just 1 over arc secant of x times the derivative of arc secant of x, which is the absolute value of x times the square root of x squared minus 1. And you can put them all down in one big fraction. There you go. Questions? And Natalie's doing the third one, which I'm going to do over here as well. I'm not sure why I had you come to the board if I'm just going to do them anyway. It's a crazy world. This is the product rule. Which one are you driving first, Natalie? The ln, the log? Excellent. So it's this over ln 4 x to the 4th minus 2x. And you can put this on top or you can put it right here. It doesn't matter. That's that. Plus, leave the log alone. Derive cosine, but that's just negative sine of the cubed root of x times the derivative of cubed root x, which is 1/3 x to the negative 2/3. Feeling good? Okay, just so we are aware, we are having a test on Tuesday. Okay? The bulk of the test is all the derivative rules. There's going to be implicit differentiation. There's going to be second derivatives of the implicit differentiation. There's going to be tangent lines. And there are 2 reviews online already. They're marked for Friday, which is tomorrow, but you can access them already if you want. Monday will be just a study day for us in class asking questions. So please take a look at those reviews over the weekend and come in with any questions, all right? The answer keys are on there too. I'm giving you everything you need. All right. So, today we're talking about differentiability, which is a topic that will be on the test. All right? So read that for me. You can see what it says. But differentiability is a fancy word for saying that you can find the derivative of the function. Okay? These notes are on mine. You can write it down if you like. Erase all your hard work here. I know. I gotta do it every single day. Okay. A function's differentiable at x equals a if you can find f prime of a, if it exists. That's it. If you can find the derivative there. Super simple. Okay? If we can find f prime of 3, then f is differentiable at 3. Pretty crazy. All right? And graphically or geometrically, what differentiability means is if it's differentiable and you zoom in on it, it's going to look like a line. Okay? Now, most functions we've seen so far have looked like a line. Most functions are differentiable that we're going to come across. Okay? Let me show you an example of one that is not going to be differentiable. Let's go to Desmos. Boom, 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 boom. Okay. So just for fun, no. Give me this keyboard. X squared. Ah, what is all this? Get out of here. X squared. There we go. We're zoomed in super far, but that's what x squared looks like, right? If I zoom in on any single point at all, look at that, it looks like a line. X squared is differentiable everywhere. It's a nice smooth curve, okay? However, if we were to graph, where's absolute value? Oh, it's right there. Check this out, okay? So let's get rid of this. Absolute value, if I zoom in on over here, look at this. That looks like a line, right? Because it is a line. That's easy. If I zoom in on this side over here, that looks like a line. That's easy. But if I zoom in on 0, no matter how far I zoom in, guess what it never, ever looks like? Never, ever, ever looks like a line. You see how that's called a corner. Okay? We'll explain that in a second too. But that's what I mean by something not being differentiable. Okay? Or not looking like a line when you zoom in on it. Now notice this. Look, if I zoom in on a point close to 0, eventually, does that look like a line? Yes. So this function is differentiable everywhere except for 0. And if you had to explain why, you would just say because there's a corner. Okay? All right. Now, there's 3 ways a function will fail to be differentiable. We just looked at one. All right? Another one, super easy to tell, is if there's a discontinuity. If a function has a discontinuity, then it cannot be differentiable. Okay? Because there's no, it's either undefined, which means there's no point to zoom in on, so it can't look like a line, or there's like a jump or a hole or something, all right? And it's not like a solid line like it's supposed to be. That's all I'm saying. So if you were given this function right here, y equals 1 over x, and I said, tell me where this function's not differentiable. All you would do is look at it and be like, I can't divide by 0, x can't be 0, the function's undefined at 0, so it cannot be differentiable at 0. So you'd write this. Not, I want to type this. Whoa. Differentiable at x equals 0 because 1 over x, yep, is undefined. Or you could say discontinuous, okay? 1 over x is discontinuous. That's also okay. Do we understand that? Yeah. Easy enough? Another example? This right here. We all know that this equals x plus 3, I hope. Yeah. Except for at 3, there's a hole. So, we would write, this is not differentiable at x equals 3 because that y is not continuous at x equals 3. Make sense? This is a pretty simple topic. There's not a ton to it. I'm going to show you everything you need to know about it today. Questions? All right. For fun, if I said, hey kids, here's some function that I'm making up. Look at me go. I'm so good at this. If I asked you, where is that not differentiable? Who can tell me the answer to that extremely interesting question? Colin, what do you think? Yeah, at x equals plus or minus 4 because? Don't have to say asymptotes, just say. There you go. F of x is not continuous there. There you go. That's what that says in my sloppy handwriting. Okay? Great. Don't look at that. All right, good. So, one way a function can fail to be differentiable is if it's got a discontinuity. All right? Let me say this. Differentiability is like continuity in that it's like an adjective we use to describe functions, the property of functions. So this function right here, 1 over x, it's continuous everywhere but 0. Do you see that? Like, that's what we talk about specific x values. It's not continuous at 0. It is continuous everywhere else. It's also differentiable everywhere but 0. It's just one point where it's not differentiable. That's all. All right? All right. The second kind of thing that can happen to us is we could have a corner. And here's 2 examples of functions that have corners. One is absolute value of x. This thing is differentiable everywhere but 0. The derivative over here is -1. The derivative over here is 1. The derivative at 0 is undefined. Okay? Because there's a corner. The same thing is happening in that other one there. That's x to the 2/3. So essentially, we would like you to be able to look at a graph and tell me where it's not differentiable. You're going to look for corners, and you're going to look for discontinuities. And one other thing, which I'll show you in 1 second. Okay? All right. What's somewhat nice about differentiability, check this out. If I asked you where is this function not differentiable, and you had no idea what the graph looked like, right? Well, you could derive it. Check this out. Y prime is just 2/3 x to the 1/3, right? Where is this not defined? At 0. You can just derive it and check the derivative. Wherever it's undefined, it's not differentiable. Make sense? Now, some functions are harder to do. Like with absolute value, it's tougher to do that, to talk about the derivative of that thing. All right? But some functions, if you, hey, where's it not differentiable? You can just derive it and see where it's undefined. And undefined for us is largely going to be dividing by 0. There's other things that could happen, but really we're looking for dividing by 0 in a Calc 1 class most of the time. Okay? So, something you will see. I'll get to that later on. The third thing that could happen is called a vertical tangent line. Okay? So, here's a graph of x to the 1/3 power. That's the cubed root of x. It looks like that. It is a nice, smooth curve. All right? The reciprocal? No, that is the cubed root of x. What do you mean? It's the inverse of x cubed. That's what you're trying to say there, okay? Okay? I got you. You're not stupid. You're ugly. You're not stupid there. All right? Okay. I can only say that to Danny because he's not ugly. See? I can never say that to Natalie. Oh my God, I'm so good at this. It's just fun. Okay. He sounds like a very intelligent individual. Now, okay? You make fun of me all you want. I'm obviously, look at me. I'm just a punching bag of insults. There you go. See, good. Very basic, though. Very basic. Way more interesting things to make fun of. Okay. If there's a vertical tangent, does it make sense? Look, I zoomed in on this point right here. You see the tangent line here would be the x-axis, or the y-axis really, right? See that? Yeah. See that tangent line? And the slope of a vertical line is undefined. And that's why that's not differentiable there. Its tangent line is vertical, so the slope is undefined. Okay? Also, if you were to derive this thing, y prime equals, you would find that it's 1/3 x to the 2/3, right? That says 2/3. Well, that's not defined at 0. So super easy to see that as well. Okay? All right, excellent. See a lot of people staring at their laps currently. What's happening? We're good? Hello. That is very interesting. All right. So, let's recap. There are 3, let me type this out so it's not in my chicken scratch handwriting. Boom, what's one of them? It could be discontinuous. Yes. What's another one? A corner could happen. Oh no. And the third? A vertical tangent. Okay? So, check this out. Hello. Just because a function is continuous, this pops up on the AP test and on functions in general. Just because a function's continuous does not mean it's differentiable. Does that make sense? For instance, this thing. That's continuous, but it's not differentiable right there, right? That's a corner. Is that okay? But if a function is differentiable, then it must be continuous also. Make sense? Okay. So we say, and you'll see this again later on, but we say, yeah, differentiability, I spelled it wrong, differentiability implies continuity. Cool. That just means if it's differentiable, it must be continuous. If a function is differentiable, it must also be continuous, okay? And we haven't really talked about any of our big theorems that we're going to go over this year, but whether a function is differentiable and or continuous matters for things, okay? So it's just like a feature of functions that we look out for. Okay. Let's talk about how we're going to handle this if we see something like this. If you see, look at this function. This is a totally fair question. Where is absolute value of x squared minus 9 not differentiable? I don't want you to derive it. I want you to graph the thing. That's how we handle absolute value right now, okay? You should know what x squared minus 9 looks like. If you don't, it looks like that. It's a parabola, right? X squared shifted down 9. That's not the absolute value. That is just x squared minus 9, okay? When you take the absolute value of it, all it does is take the part that's below the x-axis, the negative y values, and flip them up to become positive. It looks like that. You see that? So that's not differentiable at these points, which is negative 3 and 3. So you would say, this is not differentiable at negative 3 and 3 because there are corners. Make sense? We're gonna put this to the test here. All right. Don't yell this out at me. Here we go. Determine where y equals the absolute value of ln of x is not, what just happened there? One note. Is not differentiable. There we go. Take a second, think about that. Discontinuities and vertical tangents. Luckily, we all know what the graph of the natural log of x looks like, right? What's the answer to this? X equals 1. Why? Because there's a corner. Because there's a corner. That's it. Okay? It is not differentiable at x equals 1 because there is a corner. You don't need to do any work. Now, on a test or something, I'd like you to show me a graph maybe, but you know ln of x looks like this. There's 1, so absolute value looks like this. Can we handle that? Easy enough? So on our test on Tuesday, much like on the reviews that you will see, I'm going to throw a handful of functions at you and say, where is this not differentiable? You're either going to tell me, we're going to find the x values because there are corners or because there's discontinuity, okay? Or a vertical tangent, or because the derivative is undefined. All those things work out, okay? You'll see as we go through the review. Everybody good? Does this make sense? Not too crazy?
Yes, sir.
Okay, something I like to talk about with differentiability. If a curve makes a nice roller coaster, right, then it's differentiable, okay? Unless it goes straight up and down, and that would be a nice roller coaster. So I guess that doesn't really fit that rule. Okay. Anyway, well, yeah, it can't loop back on itself. You know what I mean? Because that's not a function. Anyway, corners don't make nice roller coasters. It's not a great analogy, no. It's not a great analogy, no. Okay? But basically, corners don't make good roller coasters is what I'm saying to you, okay? There you go. All right. So, this is a little weird here. Do you know x cubed looks like this? Okay, that's y equals x cubed. But when you take the absolute value of it, it just flips over this side. Does that make sense? That does not create a corner because x cubed is flat at 0. So when you flip it up, it's still flat, if that makes any sense at all. That's like a weird situation when that happens. Most of the time when you flip it up, it does create a corner. But in that case, it's horizontal at 0. So when you flip it, it's still horizontal. All right? All right. And then we're also going to face questions like this. Remember these dudes? Okay? This is a piecewise function. We talked about these before with continuity. We're also going to talk about it with differentiability. Okay? So let's think about this. We're going to have two pieces to this function, right? They meet when x is 1. Much like a very fun roller coaster, it's built in pieces. And when they meet, if that roller coaster is going to be fun to ride, or not a death trap, they have to actually meet each other, right? They have to meet each other, and they have to meet with the same slope. Cool? Like if one came in like this, and the other took off like that, that would not be good.
That would be so fun.
Okay? I don't know, that might hurt you. Okay? Great. But if one piece came in like this and stopped, and then another piece took off right there at the same exact slope and then did whatever it wanted to do, that would be nice. That's differentiable. So, essentially, what I'm saying to you is, if we have a piecewise function, if it's going to be differentiable where it splits, right, at the limits of each piece, they have to meet each other, and the derivatives have to be the same. They have to meet each other, and the slope's got to be the same. Okay? So that they line up. So when you're asked a question like this, we're going to say, well, at x equals 1, the y values have to be the same. That means that they meet each other. So when you put 1 into that top function, you get that a plus b minus 1 has to equal 2b plus 2a. Does anybody not understand where that just came from? Okay? Excellent. If that equation is true, it guarantees that those two pieces meet each other. Okay? But because that's only one equation with two variables, there are infinitely many solutions to that. They're all ordered pairs for A and B. But they're not all going to make it differentiable. Just because they meet, again, this top one's a parabola, right? Here's our parabola. Just because they meet doesn't mean they're going to meet and be differentiable, okay? So that equation guarantees they meet. I also need their slopes to be the same, so we're going to check out their derivatives. Now, this is weird to derive with these a's and b's, but remember, a and b are just numbers. We're deriving x. So the derivative of ax squared is 2ax. The derivative of bx is b. The derivative of minus 1 is 0. So that has to be the derivative of that piece. Is that okay? The derivative of the second piece. Think about it for a second. Look at it. Think in your head, what could it be? The suspense is killing us. Okay. It's not 2b plus 2. It's just 2b. Sorry. Okay? So, but that's a common mistake. Kids derive 2a to get 2. A is just a number. All right? So the derivative of 2a is just 0. All right. So that's our derivative. In order for us to match up their slopes, I plug in 1. Y'all see what I'm doing? And I get 2a plus b has to equal 2b. Questions on where that just came from? I plugged 1 into the original function and set them equal. That means they're going to meet. I plug 1 into the derivatives and set those equal. That means they'll have the same slope. Is that okay? I need both pieces. Now, this is a system I need to solve it. We could, what we usually do is we line these up and do elimination. But because this is so simple, we can just find out that 2a is b. You see that? And then we can do a substitution. So I'm going to take this and drop it into this line. Okay? And that's going to give me a plus b, but b is 2a. Is that all right? equals 2b, but that is 4a plus 2a. Okay? I want this to be like a little bit thicker. That gives us, oh, that's too thick now. Which means -1 is 3a, which means a would have to be -1/3. I know, it's so good. And because b is just 2 times a, b would be -2/3. Does that make sense? Fairly easy. So let me show you this in Desmos. Let's talk to our friend Desmos. What do we have? ax squared plus bx plus c. Yeah, Desmos. Ax. Maybe. Oh. Isn't it plus 1? What was it? I forgot already. -1. -1. Let's make sliders for these dudes. Equals 2bx plus 2a. Was that what it was? Anybody? I'm just guessing stuff here. 2bx plus 2a. Okay, check it out. I'm zoomed in super duper far. That's what that looks like, okay? However, this first piece is only defined for x less than 1. That looks like that. And this piece is only defined for x greater than 1. Now look at that. You see my two pieces? Do they meet each other? No, that's when a and b are both 1. You see my sliders over here? They're both 1. But if I slide b around a little bit and change it, I can make them meet. There you go. They meet down there, right? Sort of. But they're not differentiable there. Do you see that? Let me grab the phone. But if I make a and b equal to down they were, you're going to see it's differentiable. Smith. Hi. She is. Absolutely. Okay. If, not to ruin all the fun, if I let a equal -1/3, wow. Look at this picture. See how they don't meet? No. But once I make b -2/3, oh my gosh, they meet. I know, right? And when I zoom in on it, oh, it looks like a line. Hey. Okay? Very crazy. All right. Yeah, let's somebody walk you in. Okay? All right, and last thing, which is not in these notes. Here we go. Okay, here we go, here we go, here we go. Oh, that's not what I want. Change that. It is, look at this. Oh, it's too thick though. Okay. F of x, we can't do that's too much. Let's go back to red. No. We don't sacrifice style for substance, or substance for style, style for substance. There we go. Function over fashion, kids. Okay. Is this function, which I'm going to say is x squared minus 4x plus 1, when x is less than -1. -1 less than or equal to x. I'm maybe going to fly here. What's that going to be? 1, 5, 6. Okay, and it's also going to be -6x. Okay, there we go. Is that function differentiable at x equals 1? Here's what we're going to do. You ready? What's the first thing that has to happen? Got to be continuous. They got to meet. Thank you so much. So you plug 1 in. That's basically what you're doing. What you're really doing, though, kids, is checking the left limit and the right limit if you have to write that out. You don't say, I plugged in -1 and got the same thing. No, we talk about the left limit and the right limit, okay? But when we do plug in -1, we get the same thing unless I messed up. Do we get the same thing? We get 1 plus 4 plus 1, that's 6 and 6, right? So it is continuous. You get 1 plus 4 plus 1. Yes. So they're both 6. So here's what that tells us. at -1, they meet at 6, okay? Boom, they both go there. But then we got to check their slopes. So we check f prime of x. But you'll notice these functions, a lot of times I think kids really hate to see piecewise functions, but the functions that will be in the piecewise functions are relatively simple. They're always going to be fairly simple concepts. Parabolas and lines and things like that. Cool. Most of the time. Every once in a while you see some weird stuff. All right? Cool. So these are the derivatives. Do they match up at -1? Yeah, they're both -6, right? Cool. So you're going to say, yes, because f of x is continuous. Look at this fanciness. At x equals -1. Remember how we show that? The limit as we approach from the right is equal to the limit as we approach from the left is equal to f of -1. They're all 6. Is that okay? That's continuity. Remember that?
Yes, sir.
So that happens. And remember when I said when you plug in -1, you're checking left limit, right limit? We did that on the derivative. The limit as I approach -1 from the left of f prime of x is equal to the limit as I approach -1 from the right of f of x, and they both equal -6. That's why it's differentiable if you had to explain that. But a lot of times it's just like a multiple choice question, like where's this thing not differentiable? Okay? Great work today, everyone, especially me.